Guys, nice to see you. How are you doing? Let us recall last discussion. We introduced the concept of capacitance and capacitors. So, who will remind me what is a capacitor?
Accumulate electric charge.
Okay, so it could be either just conductor, because you can charge it, will be isolated, or it could be usually, as we know, capacitors is a system of two electrodes, and they can be of different shape, but most common are parallel plate capacitors when we have two parallel plates placed close to each other. So, what is the equation which we derived for parallel plate capacitance? Like capacitance of a parallel plate capacitor. So C capacitance is equal
Epsilon naught by area divided by distance.
epsilon naught times area divided by distance. So we see that, well, epsilon naught is a constant, so it's proportional to area and inversely proportional to distance. So the kind of intuitive that capacitance of parallel plate capacitor increases as area of this plate increases, because it's obvious you can accumulate kind of more charge. At last lecture, like after last lecture, there was a question regarding this distance d, so I believe it worth to discuss it with everyone. Any suggestions why capacitance decreases with distance? Why we have reciprocal dependence?
As we know, our capacitance depends on the electric field. So
Okay.
the distance increases, this electric field decreases.
Oh no, that is start was good, but not finish. So electric field matters here, but it doesn't decrease. So that's the thing. So the key point here, which you need to remember, that electric field is constant. We wrote the equation. Electric field is equal to what? Sigma, surface density of electric charge accumulated on these plates, divided by epsilon naught. So that is a constant. It doesn't matter how far these plates are. And even if we follow this suggestion that, let's say, we assume that electric field decreases as the distance increases, which is wrong, but let us assume this, then your potential difference should decrease, and potential difference is in the denominator for the expression of capacitance, because capacitance is equal to electric charge divided by potential difference. So in that case, if your denominator decreases, your capacitance should increase, so which doesn't fit with the reality. So coming back to constant electric field, which does not depend on the distance between plates, if we increase distance, now we have constant field, it doesn't change. We increase distance, what increases? Voltage. Potential difference between plates. Now we again recall the equation which like this describes capacitance. That's charge divided by potential difference. Charge remains the same because we just increase the distance, and potential difference increases, which is in denominator means capacitance goes down. So that's why the capacitance reversely proportional to the distance. So now we continue further with energy accumulated in capacitors, and further we will introduce a new topic, which is electric current. So as you may already understand, if we charge a capacitor, we create electric field inside this volume for the capacitor, and obviously we create some accumulate some energy in in this capacitor. So let us try to understand how much work we need to do in order to add some charge Q to electric capacitor, which is already charged with some up to some potential difference. And eventually that will help us to define, because we assume that we don't have any losses. So this work which we perform in order to charge a capacitor from, let's say, 0 to a certain charge Q, that will be equivalent to energy accumulated inside this capacitor. So that's the approach which we will take now and get these equations derived. So let's say small work which has to be done in order to add small charge dq to a capacitor with certain potential difference will be delta V, the initial potential difference, times dq. Or in other form, we can write q divided by c and times dq. So here, this q is initial charge accumulated inside a capacitor, and c in the denominator, that is the capacitance. So now if we want to get the work necessary to be done in order to charge capacitor from 0 to some charge Q capital, let's go from 0 to charge Q capital, and we need to integrate previous expression. So it will be Q over C times dQ. What do we know about capacitance? That which factors, like parameters, define capacitance and which don't. So let's say if we again recall this equation for parallel plate capacitor. So we have area and distance, and those are what geometric parameters of the capacitor. We do not have any other parameters, for instance, electric charge. So as we charge more and more capacitor, its capacitance does not change because it's independent on electric charge. If it is independent, we can factor it out from this integral as a constant. One over C integral from 0 to Q dq. And eventually we get Q capital in second power divided by 2C. So this is the expression for work needed to be done to charge capacitor with capacitance C from 0 to this charge capital Q. And obviously, if we assume that there are no losses of any dissipation of energy, that will be equal to energy of electric field created in this capacitor, means accumulated in this capacitor. So taking into account the expression for capacitance, C is equal to Q over delta V, we can write this expression for work, or also we can write it also energy accumulated, some like potential energy accumulated in the capacitor in different forms. So first is which we derived, that is Q square over 2C. Then we can write that it will be 1/2 Q times delta V, or one more option, that will be 1/2 C times delta V square. So we just consider different parameters because sometimes you are given different set of parameters, so you can use different equations in order to determine work or the energy accumulated in the capacitor. So now let us consider some specific example when we not are talking about just capacitance, but specify that we are dealing with a parallel plate capacitor. So we have a specific equation which describes capacitance of such a capacitor, and then we can consider what will be the energy accumulated in parallel plate capacitor. So for parallel plate capacitor, we remember that potential difference, dV, is given as electric field times distance between the plates. Then capacitance is given as epsilon naught times area divided by distance. So now we can substitute this in the last equation here. And for potential energy accumulated in a parallel plate capacitor, we will have the following. So it will be epsilon, like 1/2 epsilon naught times A over D, and E squared times D squared. So eventually we can write 1/2 times epsilon naught A times D times E squared. So now what is this term? Area times distance, that is volume inside the defined by the plates of the capacitor. So in this case, if we want to determine the density of electric field energy per unit volume, we just divide this expression by the volume. So we can write here UE, which stands for density of electric field energy per unit volume. So that will be capital U divided by A times D, and that is 1/2 epsilon naught times E squared. So now we have expressions in general for energy accumulated, electric field energy accumulated in capacitor. It doesn't matter what type of capacitors we are dealing with. If we know charge and capacitance, for instance, accumulated charge and capacitance of this given capacitor, we can determine the potential energy or any other combination of parameters which are given. Also, we know the equation which specifically defines potential energy for parallel plate capacitor in terms of its parameters, area, distance, and magnitude of uniform electric field inside. And finally, if we want to get density of electric field energy per unit, like means energy per unit volume, we also have this simple equation, which would be nice to remember because we will deal with it in the future too. So now let us mention about a possibility to modify capacitance of a parallel plate capacitor. So let's say we have some parallel plate capacitor with some capacitance C naught. So it's charged with some charge Q naught. We have, let's say, plus, minus. So any suggestions? How would you consider an option to change capacitance of this capacitor in order to fit some requirements which you are faced? So what is the most simple way to do it. One option, you can put plates either closer or further, depends what you want. Another option, you can change the area of the plates. Maybe you have seen such capacitors for tuning radius. There is like a system of interpenetrating plates. So you can, one set of plates is fixed, another you can rotate. And as you rotate, the overlap between these plates is changing. So means the area of the capacitor, active area of the capacitor, parallel plate capacitor is changing. So in that case, you can also change the capacitance. However, there is one more option, which is quite often used. We can fill it with some dielectric material. So what it gives us? If we fill this space between two plates with a dielectric material, then the magnitude of electric field inside this plate, because other parameters don't change, like the amount of electric charge which is accumulated at the plates, it stays the same. However, the electric field in this case will be defined as sigma, which stays the same, divided by epsilon naught times k. K is the electric constant of the material, the electric material which we use in between these plates, and it tells us in how many times the electric field becomes weaker when we place this dielectric in this space in comparison to the same electric field in vacuum. So if we replace vacuum, let's say, like fill vacuum with some material, that dielectric constant as a property of this material defines how many times we reduce magnitude of electric field. And usually we deal with k values. I'm actually always larger than unit. So vacuum has dielectric constant of unity, and air is very close to unity, so it's like 1.0 something. But there are different materials which possess the electric constant equal to 10, 20, 100. So you see that with such materials, you can significantly reduce electric field inside the capacitor. So now if we reduce electric field inside the capacitor, what happens in terms of potential difference? So initially it was delta V naught in vacuum. Then we filled it with some dielectric material, and delta V is given as delta V naught divided by K. So why? Because we have electric field naught, like magnitude of electric field in vacuum before we filled it with dielectric, times distance, and new electric field is K times smaller. So we need to divide this electric field, initial electric field, by K. So in this case, we decrease the potential difference by K, in K times. So as a result, we remember, we had this discussion at the beginning of the lecture, potential difference stays in the denominator for capacitance. C is equal to Q, which is constant, doesn't change, over delta V. And if we go, so this is, let's say, for initial case, when we have vacuum inside. But what will be for capacitance after filling the space with the dielectric material? So we will have Q naught, that will stay the same, but instead of delta V naught, we will have delta V, and that is Q naught over delta V naught and times K. This is
this ratio is C naught. So we end up with K times C naught. So what we get here, if we replace the field vector in between these plates with the electric material, the electric constant K, then we increase the initial capacitance in vacuum by factor of K. So that is the way how we can modify capacitance of a capacitor. And also we need to consider here few options. What happens if we don't fill the capacitor completely, like this space between plates completely, but only partially. So let's say we have a parallel plate capacitor, and here is vacuum inside. So we place some dielectric plate here. So the thickness of this dielectric plate is A, and the total distance between plates is D. So if we charge now this capacitor, we polarize the dielectric layer, and now we can consider this system as two capacitors connected in series. So that will be something like this. Will be plus, minus, plus, minus. And these two parallel plate capacitors will possess the distance between plates as d minus a over 2, and here the same d minus a over 2. So now you can calculate capacitance of each of them, and then use the rule of calculating the equivalent capacitance of two capacitors connected in series, and that will give you the equivalent capacitance of this system, which we considered here. So another example, if we have parallel capacitor, there is some distance d between the plates, and then we fill it with a dielectric layer like this. So it's in contact with one of the plates, but doesn't fill the whole space between the parallel plates of this capacitor. So now we can claim that this and this thickness will be some coefficient f times d, and here it will be 1 minus f times d. So we have dielectric material with some dielectric constant k, and here in this part we have just vacuum. So we represent it as a system of two capacitors connected in series also. First capacitor will be filled with the dielectric material, the electric constant K, and its thickness will be F times D. And here it will be just empty space between two plates, and their distance will be 1 minus F times D. So again, you calculate capacitance of each of these components of the battery of capacitance and apply rule for equivalent capacitance calculation when we have two capacitors connected in series. So with this, we switch further and consider electric current and give introduction to this topic. So what would you understand under electric current?
Movement of the charge.
Well, they need to be more specific in this case because movement of charges happens always. Let's say if we have a metal, in metal we have plenty of free mobile electrons which are charge carriers. They are negatively charged. And because of thermal motion, they continuously are moving with quite high speed.
Directed.
Exactly. So we need to specify that this is a directed motion of electric charges. That's electric current. And let us consider this example when we have some positive charges, let's say, some cross section with area A, and these charges are moving through this surface. So the average current, like magnitude of average current, is given as a rate with which electric current is the electric charge is passing through this surface. So that is delta Q, total charge, which passed through the surface over some time interval delta T. So that's definition of electric current, and we like the units for electric current. These are coulomb per second, and that for that we have a special unit which is ampere, A. So 1 ampere means that we have transfer of 1 coulomb per 1 second through some given surface. If electric current is a function of time, then we are talking about some instantaneous value of electric current. And in this case, I is defined as first derivative of Q, charge over time, dq over dt. So let us understand what is the reason for these charges to move actually. So far we considered conductors under electrostatic equilibrium. And the key condition there was that under electrostatic equilibrium, we do not have any electric fields inside the conductors. If there is no electric field, no electric force which acts on charges. They can be mobile, they can move with some in random directions with thermal velocity. However, they do not have some dominant directed motion because of external electric. In order to have electric current, in order to create such conditions, we push these conductors out from electrostatic equilibrium and create internal field inside the conductor. So if we have electric field inside the conductor, there will be some electric force directed either along electric field vector or opposite, depends what type of charges we have. If, for instance, we have electrons, that's the most common case for conductors because we mostly deal with metals. So in that case, where will be electric field force? In the same direction or in the opposite electric field vector?
If it wasn't forced. So we have electrons, they are negatively charged. We create internal electric field, like inside a conductor, and obviously there will be electric force acting on these negatively charged electrons. This electric force vector will be in the same direction to electric field vector or in the opposite.
In opposite.
In opposite because we have negative sign of the electric charge. So then what happens? We exert some electric force on electrons. They start to move with acceleration. But obviously they cannot accelerate forever because as they move, they will hit some ions in the crystalline lattice of this metal and dissipate energy. So there will be some equilibrium established between interacting, dissipating energy to the crystalline lattice of the metal structure and energy which these electrons are gaining because of electric field performs some work. This electric force performs work in moving them. So that's why they will gain certain directed uh, along electric field or in opposite direction, depends on the charges, um, velocity, which is called drift velocity. So directed velocity of electric charges in the direction or opposite to the direction of electric field vector will be called drift velocity. So with this drift velocity, so this is you need to distinguish drift velocity and thermal velocity. Thermal velocity can be very high. It can be hundreds, like thousands and more. It depends on temperature, centimeters per second. However, drift velocity usually is quite small because you need to force all these charges to move in the direction of electric field. So thermal velocity can be high, but random orientation for each of electron, it will be different. But drift velocity is small usually because we are dealing with, let's say, reasonably high electric fields. But all vectors of this, for all electrons, this vector of drift velocity will be oriented in the same direction as opposite to thermal velocity. So now let us consider some microscopic model of electric current. Let's say we have a conductor and consider two cross sections of this conductor. So area of these cross sections is the same. It will be A. And we have some positive charges here. So positive charges Q, and they move with some directed drift velocity Vd. So this distance is some delta x. So let's assume that this is along axis x. So now what will be the whole electric charge accumulated in this volume of the conductor defined by these two cross sections? So we need to multiply area of the cross section by distance between two cross sections. So that gives us the volume, but in order to determine the whole charge which is accumulated there, we need to consider also density of these charges, like how many charges per unit volume are inside this conductor, which can participate in charge transport.
and obviously a magnitude of these charges. So we assume that all charges possess the same magnitude, it's some magnitude q, and that's why the total charge which is placed in this volume, delta q, will be defined as density of charges, like number of charges per unit volume, times area times delta x, and everything we multiply by q. This is the magnitude of a single charge. So now what will be this delta x? If we consider this process of charge transport within some time interval delta t, so we can express it as vd, drift velocity of electric charges, times let's use here delta t. So this is the time interval which we consider. So now we can substitute it to the equation for electric charge, and that will be n times a times vd delta t times q. And according to the definition of average electric current, average is delta q over delta t, we can write that electric current, like average magnitude of electric current, will be n times q times vd times a. So there are several parameters which define electric current, and this is the density of electric charges, like mobile electric charges, which can participate in charge transport once we create internal electric field inside the conductor. Magnitude of electric charge, of a single electric charge which is mobile. The drift velocity. Obviously, this will be a function of electric field, first of all, because that will define how much we will push these charges to move in a given direction, but also it will include information about materials properties, which specify how easy charge carriers in given material can move through it inside. So different materials will possess different features in this aspect. And here is the area. So area is not a very material specific feature. So usually it's quite common to operate with current density. So we have J average. So average current density, that is current average divided by area of the conductor. So we end up with N times Q times VD. And obviously for the current density, the units will be ampere per meter square. It's current density. Yes. So now let us introduce the Ohm's law. First, we introduce it in the differential form. So we can write, so we have this expression for current density in terms of charge carrier concentration, magnitude of electric charge, and drift velocity. However, we can express it in a different form, which is quite commonly used because it's more practical form. So current density J is equal to sigma times electric field. So sigma in this case, it's already not surface density, but this is a new parameter which is conductivity, specific conductivity of the conductor. And if we multiply this by magnitude of electric field, we get the current density in the conductor. So now, and obviously this is a specific feature of the material, so different conductors will possess different values, so magnitudes are tabulated for different materials, so you can easily find these magnitudes for specific electrical conductivity. By the way, who knows which metal possesses the highest specific electrical conductivity? What is the best conductor? Okay, at least you know many metals, but you don't know which one is the most conductive. So actually, it's silver. Gold is quite close and commonly used in electric circuits, but because of inertia, so it doesn't oxidize and it doesn't change its properties over time. So contact, specifically when you have some uh, mechanical contact between two conductors, you don't want one contact to be oxidized, because then there will be no contact. And that's why all this, like for instance, if you check on the sockets for CPU, like central processors, there are many like legs, these electrical contacts where you connect to motherboard, and all of them are covered with thin layer of gold because they stay not oxidized. However, in terms of specific electrical conductivity, silver is the leader. In terms of copper and aluminum, those which are commonly used in electrical like wire systems, like electrical network. However, specific conductivity of copper is noticeably higher, and that's kind of preferable, because otherwise, in order to have the same resistance, you need thicker aluminum wires, and sometimes it's not practical. So copper is it's the cheapest, most technological, and quite conductive material. That's why it's used pretty much everywhere. But silver conducts better. So now let us consider a cross section of a conductor again. So this is some piece of conductor with length of L. Here we have potential VA. Here is potential VB. This is the electric current, and this is area, like cross-section area of this conductor A. So we have some internal uniform electric field E inside this conductor. So now what will be the potential difference? Delta V. Since we have uniform electric field, we can just multiply E by L, the length of this segment of the conductor. We know from Ohm's law in differential form that J, the current density, will be specific electrical conductivity sigma times electric field, like magnitude of electric field. And that will be sigma times delta V over L, according to previous equation. So now let us express delta V from this second equation. So that will be L, the length of this segment, divided by sigma times J. Now we can also write that it will be L divided by sigma times A, which is area of the cross section. And here, instead of J, we already need to put I, because that will be just current. So this combination here, maybe I will write it in different way so it will be more clear. So we can write like I over A. So this is J. And eventually we have L over sigma times A times I. So this part here is called electrical resistance. So that is denoted as capital R. So we can write that the potential difference between 2 points in conductor will be defined as a product of electrical resistance of this segment of electrical conductor between given 2 points times electric current which flows through this conductor. So R times I. So units for electrical resistance are voltage over ampere, and we have special units for that, that is ohm. So let us summarize our discussion for today. And we consider the energy accumulated in capacitor as we charge it from 0 to some charge Q. We determined what will be this energy specifically for per plate capacitor, and also determined the density of electric field energy per unit volume. So we consider options to increase capacitance of a capacitor by filling the space between empty space between the plates with some electric material, the electric constant K, and we have shown that capacitance, like new capacitance increased, will be equal to K, the electric constant, times initial capacitance C naught, which this system of two parallel plates possessed before we filled the space with the electric material. So we introduced the concept of electric current, which is the rate of charge passing through given area, and have shown that in general, electric current will be defined by, so if we are talking about electric current density, which is current divided by cross section of the conductor, will be defined by concentration of charge carriers and magnitude of electric charge of each charge carrier and their drift velocity. Drift velocity is the directional motion of electric charges along electric field. Don't miss it with thermal velocity because it's random oriented velocity much higher usually than drift velocity, and this velocity is always for each charge areas has the same direction. We introduced the Ohm's law in differential form, which is J current density equals to product of sigma and electric field, like specific electric conductivity and electric field inside the conductor. And using this Ohm's law in differential form, we also introduce the expression for electrical resistance of a segment of electrical conductor. So we see that electrical resistance will increase proportionally to the length of this conductor. Obviously, the more material, the longer our conductor, the longer distance charge carrier should pass. They will experience more resistance from going through this material, and that will contribute to higher resistance of this segment. And it's reversely proportional to area. So the larger area of the cross-section area of the conductor, obviously it will be easier to pass through it. And also this specific electrical conductivity, which is a unique feature of the material. Each conductor will possess its unique value for specific electrical conductivity, and it depends on the material structure. And now you know that silver is the most possesses the highest circular flow. Okay, thank you very much for attention. See you next time. We will continue with electric current on Friday. Have a good evening.